So this is what we were looking at, basically how to handle data dependencies. I'm going to finish this, and then I'm going to move to precise exceptions. And if time permits, we will go a little bit, we will have a little bit more fun with control dependence, which is branch prediction, which is a topic that's fascinated many, many people. But I don't know if time will permit. Let's see how far we can go. So I updated this based on the discussion we had yesterday. Basically, you need to detect dependencies in some way. There are 6 fundamental ways of handling flow dependencies. I said 5 yesterday, but it's true that there is another way if you actually detect the dependence, which is the out-of-order execution part, which I was not considering in the slides because we were talking about pipelining. But to be precise, I added that 6th way over here also. Basically, we talked about all of these, detecting and waiting, detecting and forwarding, detecting and eliminating the dependence at the software level. We'll talk about detecting the dependence and moving the dependent instructions out of the way such that you can execute independent instructions, which is out-of-order execution. That's next week. And we briefly talked about predicting the value, and we talked about doing something else where you don't need to detect at all. So these are very fundamental ways. They all have their principles and they all have their trade-offs. So let's talk about we finished with the stalling part. Basically, there are some dependencies where you can detect, but you cannot forward the value because the pipeline is structured in such a way and the latency of an instruction is in such a way that even if you forward the value, it's just too late for the previous instruction to capture it before it starts executing. This was the example with this load instruction, right? Load instruction produced its value at the end of this memory stage, and the AND instruction needed that value while that value was being produced, meaning while the load instruction was accessing memory, AND instruction actually required that value to execute in the register, to execute in the ALU stage. I should have had the previous slide, but basically, that's impossible to do unless you extend the clock cycle. If you remember the discussion yesterday, if you extend the clock cycle, get the data from the load and supply it to the beginning of the ALU in the same cycle, that's a bad idea. Now you actually have 2x the clock cycle potentially. So in this case, we did need to stall the pipeline, stall the AND instruction, which is shown in this figure basically. This load generates its value, results, at the end of this memory stage and latches the result, and that result is immediately forwarded to the ALU stage such that the AND can execute, but AND has to wait for 1 cycle over here. So there are cases where you cannot forward the data because of the pipeline structure in this case. If you design your pipeline in some other way, you could potentially have forwarded this data, but then there are trade-offs, right? Again, maybe your clock cycle would be longer. Maybe there are ways where you could execute this load faster. I don't know. The problem is really load takes 2 cycles, right? The reason this is happening is load requires this stage and this stage. And it really takes 2 cycles to execute. 1 cycle to generate its address, 1 cycle to access memory. Whereas AND doesn't require 2 cycles. It just requires 1 cycle, and it just basically does nothing in this stage over here. So it's really a pipeline structure issue and the instruction latency issue. Okay, how do you support stalls? We've discussed this before, but let's look at it again. I told you about a structured way of doing it also. Basically, you add enable inputs to the fetch and decode pipeline registers, and you can add a synchronous reset or clear input to the execute pipeline register. Basically, this is just an overview. This is one way of doing it. Basically, you reset the pipeline register such that the stalling stage doesn't move but injects a no-op into the next stage, such that basically, essentially you're propagating a bubble through the pipeline. It's a hardware inserted no-op. And you basically ensure that you don't latch anything into the previous pipeline registers. The fetch stage, program counter, they have to stay there because the pipeline is not moving, right? That is done using the enable inputs. This could be done using clearing, or it could be done using an invalid bit associated with each pipeline register, whether the contents are valid, or the contents should update the architectural state when they go down. This is a more principled way, as I said. It's always good to think about principles, going back to lecture 1 and 2. Why it's a principled way? Because you can look at the pipeline, examine it, and say, oh, this is invalid, this is invalid, this is valid, this is invalid. As opposed to checking all of the control signals and understanding or interpreting that this is a no-op. This is not supposed to take effect. Okay, so when a load stall occurs, you assert the stall decode and stall fetch signals to ensure that decode and fetch stage pipeline registers hold on to their values. They don't overwrite, they don't get overwritten. And you assert flush execute stage to clear the contents of the execute stage pipeline register, introducing a bubble. Basically, if you look at this, you can examine the slides as to listening or reading also from Harris and Harris. Basically, these stall signals are asserted such that you don't latch you don't overwrite the latches, and you basically flush the execute stage. You basically insert a bubble over here instead of moving the AND over here. Okay, that's hopefully simple. It'll get much more complicated next week. Okay, is there anything else I would like to say over here? Not really. That's basically it. It's stalling logic. Let's look at control dependencies just a little bit. This is, I don't want to open up a huge area because there's a lot of stuff to consider talking about control dependencies. But this is, as I mentioned, it's a special case of data dependence. It really depends on the program counter. Let's look at the branch equal. The problem with a branch is the branch condition is not determined until the fourth stage of the pipeline. Right? If you remember, machine, basically the pipeline determines the branch condition over here. Now you could make it earlier, as we will see in a little bit. But you do need that condition, you do need the target address much earlier, right? Because you need to figure out what's the next instruction to fetch. One obvious, very simple prediction mechanism, as we discussed yesterday, is predicting that branch will not be taken. Basically, branch will not jump to the target address. It will fall through to the next sequential instruction. This is called a fall through. A taken branch goes to the target address, a non-taken branch or not taken branch falls through to the next sequential instruction. So if you assume that the branch will not be taken, you keep the pipeline full with the sequential instructions in the sequential instruction stream. PC plus 4 in MIPS. In x86, you need to figure out the instruction size of the branch and add to it. So basically, you can fetch the instructions after the branch, before the branch is resolved. If you're correct, everything is good, because branch is not going to change the program counter to the target address. But if you're incorrect, basically this is always predicting that the next sequential instruction is fetched. It's also called always not taken prediction. If you're correct, that's good. But if you're incorrect, which means that the branch is taken, now you need to flush the instructions. When you determine the target address of the branch, what you do is basically flush all previous pipeline stages, change the program counter to the new correct target address, and refetch instructions from the correct path. Now clearly this can involve a lot of wasted cycles, right? In this case it could be 4 cycles, but if your pipeline is 20 deep, and if you determine the branch condition at the 19th stage, you lose 19 cycles. And a 20 deep pipeline existed, it still exists actually. Pentium 4 had a 20 deep pipeline, it had 25 pipeline stages. Later versions of Pentium 4, it's called Prescott, had almost 30 pipeline stages, actually. So branch misprediction penalty is the number of instructions that are flushed when the branch is taken. This is basically wasted work, or wasted opportunity to improve performance. Right. Okay, so this could be, there are many ways of reducing it. Of course, one way of reducing it is by getting rid of the mispredictions, right? By having a better prediction. So we're not going to talk about that as much right now. If you have time later on today, we'll talk about it. If not, you can take the more advanced course. And this is really exciting stuff, if you will. Always not taken is a bad idea in general. Actually, I'll give you a lot of data averaged across many applications in the world suggests that if you do always not taken prediction, your prediction accuracy is about 30%. So 70% of the branches are actually taken. And maybe you can guess why. Let's see who's a brave one. Can anybody guess why? Yes. Yes, exactly. Loops, basically. Because a lot of programs are structured as loops, and a lot of programs iterate a lot over the loops. So if you actually have a loop branch, it's a good idea to say, oh, it's going to be taken, because I'm going to go back into the loop and do it over many, many elements of an array, for example. So actually, always taken prediction is much better than always not taken. But of course, now you can start being smarter, right? You can say, oh, why don't I distinguish between different branches? Maybe this branch is always taken, this branch is always not taken. So now, based on the program counter, I have separate predictions. Now it starts getting exciting and more complicated also. But what if it's not always taken or always not taken, but it's taken dependent on something else in the program? So a lot of processors today actually try to figure out whether a branch is taken or not, going to be taken or not taken, or guess, based on the past history of the branches that have been seen in the program. So they keep history of taken or not taken the directions of different branches or the same branch, and based on that they decide, oh, when I fetch this branch it's going to be taken or not taken. Of course, it's a little bit more complicated because there are different types of branches also, so processors try to classify branches as loop branches, as other kind of branches, hard to predict branches, easy to predict branches. So if you look at the branch prediction logic in an existing microprocessor, take Intel Core architecture, it's actually a huge piece of structure. And it needs to be optimized really well because you need this prediction in one cycle, really. In a single cycle, you do need this prediction and feed it back to the program counter, right, to fetch. Okay, I just hopefully gave you a glimpse of the complexity of the problem. Okay, 30% we'll do with 30% for now. But we want really 99%. We actually want 100%, right? Okay, so basically, so you can reduce the effect of branches by doing better prediction, or you can reduce the effect of branches by reducing the branch misprediction penalty, right? So if you mispredicted, okay, maybe it's better to reduce the penalty that you have. Instead of having 20 cycles, you make it 10 cycles. Well, instead of having 4 cycles here, why don't we make it a little bit lower? So instead of determining the branch over here, let's add some logic early on in the pipeline over here to determine the branch over here. If you determine the branch over here, if you have a misprediction, only this part will be wasted, right? So ideally, you would like to determine where the branch goes right in this stage. When you fetch the branch, while you're fetching the branch, you need to say the next target address should be the target, or next sequential instruction. So really, when you're fetching the branch, you need to do this prediction. That's why this is very tight. But we're not going to go through that right now. We're going to say, instead of determining the branch over here, let's resolve it over here. Well, okay, before that, let me give you the downside of determining the branch over here, right? So we're determining the branch over here, which means that this branch resolves at the memory stage. Remember, this is a branch equal, so you need to test the equality of T2 to T2 and T1 over here. And if they're equal, then you jump to the target address, right? So this, you do that computation over here, and then latch the target address, latch the condition, and based on that condition, you need to redirect the fetch engine. But you've already fetched 3 instructions over here. If the calculation says that you should jump to the target, you need to flush these 3 instructions and redirect the fetch stage to the correct program counter over here. That's what this is showing. So you basically wasted 3 instructions, right? If you determine the branch a little bit earlier by adding specialized logic like this, basically you know the register values, right? If you look at, this is source register 1, source register 2, you need to check the equality of those. Basically we add specialized logic that checks the equality of those source register values, and if they're equal, then we add special logic that selects the target address from this target address computation logic, right? So this is where we computed the target address. We kind of moved that over here also, right? This is where previously, this is where we computed the target address. But there's no reason we cannot compute it earlier. So we moved the target address computation earlier, and we moved this equality check earlier also. That way, you can actually compute the condition of the branch as well as the target address of the branch in the second stage. Right. This is called early branch resolution. This is employed in many processors actually, in maybe not in this not so great way. And I'll ask you why. This is not that great. But basically you're introducing another data dependency in the decode stage over here. So if you do this, if this is fine, now you reduce the branch misprediction penalty, right? Because you compute the branch target address and the condition over here, and if it's not the next sequential instruction, you can redirect the program counter to the correct target address, and you just need to flush one instruction, because you fetched only one. Right. Okay, this is good, that sounds great. Now, as with everything else in engineering, and especially computer architecture, there are advantages and disadvantages to this. Well, I'll give you the advantages. Clearly, I've given you one advantage, right? You reduce the branch misprediction penalty. Basically, you reduce the cycles per instruction, because you reduce the cycles wasted when the branch is mispredicted. What about disadvantages? Anybody tell me? Yes? Exactly. Additional hardware is one of them. There's additional hardware cost, because you replicated that equality check logic. You could have done that in the ALU, right? What else? There are multiple. Yes?
Introduce a new data dependency.
That's right. Basically, you've introduced another data dependency over here. If you want to do it right, you need a new forwarding path, which translates into additional hardware. There's one more, which is similar to what you've seen earlier. Yes? Exactly, yes. You may have messed up your critical path here, right? Basically, now it's not only register read, but you've added an ALU operation, equality check operation here, and this may be your critical path. You read the registers and then do an ALU operation. Basically, those are, and then power consumption. But there could be potentially increasing clock cycle time, critical path, may or may not be, depending on what's your critical path. So maybe you get a higher, well, that should, yeah, higher time, clock cycle time, additional hardware cost. And this hardware cost is specialized and likely not used by other instructions also. And also everything else that comes with this additional hardware cost, right? Which is power consumption. Okay, so basically you need the data forwarding for early branch resolution, because if the branch depends on, right, the next instruction, this just doesn't work, right? Because you don't have the data forwarded to this stage. So you need additional data forwarding paths from this stage, as well as this stage, as well as this stage. Well, this stage you don't need, because we assume that whenever you write to the register file, you write in the first half of the clock cycle, and whenever you read in the second half of the clock cycle. Again, which may or may not be a good idea also, depending on your critical path. Does that make sense? So as you move computation early, you need to move the data forwarding logic early also. So if you want to keep the pipeline moving, again, otherwise you may not get the full benefit of doing the branch resolution early. Okay, cool. I'm going to skip this. You can, basically this is just some Verilog code that shows how you actually design the stage. But hopefully you can do this in your sleep soon. Yeah. Or you'll get there. Okay, so doing better. Basically, what else can you do? As I said, we can guess whether the branch will be taken. So far, we haven't guessed that. And I've given you the idea. Basically, backward branches are usually taken because they're loop branches, and loops usually iterate more than once, more than twice. In fact, you can imagine a 1,000,000 entry array, and you iterate the loop 1,000,000 times, right? So if you predict not taken, you get it right only once out of 1,000,000. If you predict taken, you get it right 1,000,000 minus 1 divided by 1,000,000 times, right? Okay, or you could consider the history of whether a branch was previously taken or not taken. This could work well. If the branch is taken, let's say, 4 times in a row and then not taken once in a row, it could happen also, depending on the structure of the loop. Maybe you can adapt to that pattern, right? Maybe you can recognize that pattern, and you can actually predict that. People have proposed learning methods, machine learning methods, to actually predict branches. They use something called perceptron. I don't want to go into a perceptron right now, but perceptron is a very basic mechanism to learn from the previous history. So if you actually train the weights of your previous history, you can basically predict better into the future. Okay. So a good prediction reduces the fraction of branches requiring a flush. So that's good. So let's do some performance analysis. I'm going to go through this really fast because you can look at the slides and do this on your own. It's number crunching mostly, but I'll give you the less number crunching parts that are interesting. So this is one way of doing performance analysis. You can take some benchmarks. Spec integer 2000 is a really old one. I should update this to 2006 maybe. Actually, I will do that right now. So people come up with benchmark suites for general purpose processors. There's an organization called SPEC, which is basically Standard Performance Evaluation Corporation. And they come up with benchmark suites, and the last benchmark suite that they came up with for microprocessor performance was in 2006, which is actually interesting, right? 2006 is how many years ago? Almost 12 years now, right? In fact, they started doing this in 2004, so it's really a 14-year-old benchmark suite. Some programs are still used, clearly, but benchmarks evolve, workloads evolve, so this is not necessarily representative. But let's assume that out of all the programs that somebody decided to deem important to evaluate your microprocessor performance with, this is the instruction mix that you have. 25% loads, 11% branches, which is usually, you're lucky if you have only 11% branches. x86, for example, usually has a lot of branches. It's 1 out of 4 instructions is a branch, usually. Of course, this depends on your ISA as well, right? And R-type instructions, these are the operate type instructions, 52%. Somebody came up with these numbers, let's say. So let's suppose that 40% of the loads are used by the next instruction. Basically, the next, there's a data dependency between the load and the next instruction, which means that you need a stall. 1 cycle stall after that. So you didn't have a very intelligent compiler, maybe. And 25% of the branches are mispredicted. And all jumps flush the next instruction. So we're assuming early branch resolution here. The question is, what is the average CPI? So you can, with this information, you can do this calculation on your own if you wish. If we had time here, I would have asked you to do it. But let's go through it very quickly. Basically, the cycles per instruction of a load is 1 when there is no stall after it. But it's 2 when there's a stall. Basically, a load essentially takes 2 cycles. You have 1 penalty cycle after that, if there is an instruction that comes right after it. So the CPI of a load is 60% of the time there's no instruction after it, so you have a 1 cycle load finishing. But 40% of the time you basically essentially are extended the load time to 2 cycles. So its CPI is 1.4. For a branch, 75% of the time you finish it in 1 cycle. 1 cycle because we're pipelined, right? We're not finishing the entire branch in 1 cycle, but we're pipelined. We're really not affecting any other flow in the pipeline. In an ideal pipeline, you finish 1 instruction per cycle. So if you think about this calculation, in an ideal pipeline, a load takes really 1 cycle. But there's an unideality when it's followed by an instruction that's dependent on it. There's a no-op or there's a bubble that you need to insert. That's why it takes 2 cycles in that case. Branch in an ideal pipeline takes only 1 cycle. The ideal in this case means you predict it correctly, and that happens 75% of the time, as I mentioned to you in the previous slide. In a non-ideal pipeline, you mispredict it 25% of the time. It takes 2 cycles, so its CPI is 1.25. So if you want to calculate the average CPI across all instructions, what you do is you take the CPI of the instruction times the fraction of that instruction in the entire instruction mix, which is from here. And we've already done the load, branch, stores, jumps, and R-type instructions are always constant latency. Jump is an unfortunate one because it takes 2 cycles, right? Because we resolve the jump. Jump is always taken, right? Here we're predicting always not taken, so we're always mispredicting the jump, if you will. But we're resolving it in the second stage with the early branch resolution mechanism. So if you do this calculation, your average CPI is actually pretty good, 1.15. That sounds good, right? Okay, so of course, when you're doing performance calculation, CPI is only one portion. clock cycle time is another, number of instructions is another. We're assuming number of instructions is constant here. You cannot assume that if you change the program with the compiler, right? Okay, 1.15 over here. So let's look at the pipeline performance. Again, I'm not going to go through this, but we've done this similarly early on for single cycle and multi-cycle machines. I'm going to point something interesting here. Basically, you need to calculate the critical path of all stages, and you need to find the maximum of it. Of course, the operation speed depends on the slowest operation or slowest stage. And remember, we had an assumption over here. Decode and write back use the register file and have only half a cycle to complete. That is why there's a 2 in front of them, basically. They really need 2x cycles to finish. Because you're assuming that you finish that operation within half a cycle after the write back completes. Now that will turn out to hurt us. If you look at this equation over here, decode stage is actually very long. Why is it very long? Because I know the next slide. Next slide gives you the latencies of these different numbers over here. Of course, this depends on your design. But assuming these latencies, it turns out your critical path goes through the decode stage, which means that you have a really bad design. If you have a decode stage as your critical path in your pipeline, you should rethink your pipeline. That should almost never be the case. In my experience, there is no design in the world that's limited by its decode. Fetch, I understand. Memory access, I understand. I can tell you that you have a good design. But if your design is in, the critical path is in your decode, then rethink. Okay, maybe we've done something bad. What have we done bad? I think I'll give you 2 reasons why this may be bad. One is we've done this early branch resolution in the decode stage, which extended our clock cycle. It's not clear if that's a good idea, because now our clock cycle is bottlenecked by decode. So if you want to look at your performance analysis again, maybe you do that branch resolution somewhere else. Now that changes your CPI, that changes your clock cycle time, and you look at your execution time again. Well, we'll look at execution time in a little bit. And then you figure out whether your execution time improves. The second thing that we've done over here is this assumption that we had. You write to the register file in the first half of the clock cycle, which means that you really don't do anything in the decode stage during that first half of the clock cycle, because you need those register values. It's really a forwarding path. And then in the second half of the clock cycle, you read from the register file and do everything else that's needed with those registers. Now that extends your clock cycle, because you're really trying to do 2 things in one clock cycle, writing and reading. Maybe there's a better way of handling that, right? Okay, so the decode stage, but we're assuming that decode stage is your critical path over here, 550 picoseconds. If you do the calculation of the execution time, it's number of instructions times CPI times clock cycle time, and if you do this calculation, you get 63 seconds. Now, if you remember a few lectures back and compare this to single cycle and multi-cycle, it's much better. So we've designed a good pipeline processor. We improved performance, but we could have done better probably by better balancing the pipeline stages. So we got 50% performance improvement over single cycle. Remember, multi-cycle was bad because of various reasons that we've discussed. But clearly we've pipelined we have 5 pipeline stages, but we didn't get 5x the performance. Our pipeline efficiency is terrible actually, right? It's only 1.5. Well, you can think about why that is the case, right? Basically, this is always true. It's very difficult to get 5x improvement with pipelining. But this is also on the lower side, in my opinion, so you really need to rethink the design of the pipeline a little bit if you get numbers like this when you design a processor. Okay, any questions? Now we've done the performance analysis. Now, if you want to actually redesign the pipeline, you go back through all of this performance analysis. Your CPIs change, for example, if you change the forwarding paths, and your cycle time changes, and you might get a better pipeline design that actually bring this up to 2x. That's the beauty of architectural design. Now we have a lot of trade-offs to deal with. But your cost may change also. We're not evaluating cost over here, right? Okay, some questions to ponder. So we have a lot of interesting concepts that we've covered, and we're going to cover even more. I'm not going to answer all of these, but I think it's always good to think about what is the role of the hardware versus the software in data dependence handling. So if we punted some of these things to software, maybe we could have done better in terms of our clock cycle time, right? It's certainly possible. Or we could have done better in the load stalls that we see. So now you know software-based interlocking and hardware-based interlocking. Basically, these differ in who inserts or manages the pipeline bubbles. If you have software-based interlocking, software inserts no-ops for pipeline bubbles, if no-ops need to be inserted, or if the software is smarter, the compiler or the programmer who programs an assembly is smarter, they would define independent instructions and insert them over there such that you don't do that. Hardware-based interlocking, hardware can do exactly the same thing, except it inserts a bubble, or it finds independent instructions also, as we will see next week, right, to execute. So who finds the independent instructions to fill the empty pipeline slots? That's basically depends on who does this, and you can always combine these also, right? It's not, so the hard approach is software does everything, or hardware does everything, but there is a middle ground somewhere in between as well, right? You basically design both to fill the pipeline slots. And there are disadvantages and advantages of each, clearly. Pain to the hardware designer, pain to the software designer being one of them. That's always the case. But also complexity in terms of hardware complexity versus software complexity. And that's always a trade-off. And think of the performance equation as well. Basically, if you actually, so if, for example, software does the interlocking, inserts the pipeline bubbles, you're really increasing the number of instructions, right? You're not touching the cycles per instruction, but you're increasing the number of instructions. Whereas if the hardware is inserting the pipeline bubbles, you're really changing the cycles per instruction without changing the number of instructions that are coming into the machine. In the end, your execution time may be the same. Okay, so some more questions to ponder. I guess this is a very similar question. What is the role of the hardware versus the software in the order in which instructions are executed in the pipeline? I'll give you some terminology. So if you actually do software-based instruction scheduling, this is called static scheduling. Static meaning before runtime, before the program runs. Whenever you hear static, it's before runtime. If you do hardware-based instruction scheduling, it's called dynamic scheduling. Dynamic means at runtime. Now there are trade-offs between these. Basically, static doesn't have information that's available to you at runtime, right? For example, if you want to predict the direction of a branch, you have no idea if you're doing it at the software level, and if we have time, we'll cover that. If you're doing it at the software level, you have no idea where which direction previous branches went, right? Because you don't have that information. You generate the program before the program runs. If the hardware does the scheduling, if the hardware does the branch prediction, it can say, oh, I can collect information as the program is running. It's already running. It's too late for the compiler or the programmer to do anything. But the hardware has a lot of information. It can collect lots of information about, for example, whether loads are followed by dependent instructions, right? It can say, oh, I'm going to do something else for that. So this impacts different metrics, clearly. Performance and parts of the performance equation, as we discussed. Complexity, where the complexity is pushed to. Is it pushed to the software or the hardware? Power consumption. So if the hardware does dynamic scheduling, like out-of-order execution, power consumption actually increases significantly. But if the software does it, you really expend the power early on when you're compiling the program. But while you're running the program, hopefully the hardware is simpler. That was, again, the philosophy of MIPS, right? Reduced instruction set computers also. Reliability, I mean, that's something for you to think about. This is, these are supposed to be open-ended. Okay, let's talk a little bit more about this because we're going to come back to this next week. So in the software-based scheduling of instructions, compiler orders the instructions and hardware executes them in that order, right? As we've discussed last time, compiler can find independent instructions. So in dynamic scheduling, hardware executes instructions out of the compiler specified order. But as we will see soon, hardware needs to reorder the instructions such that it's reported to the software in the compiler specified order. So the problem is, if you want to do software-based scheduling, somehow you need to know the latency of each instruction. Now, this is good if the instructions take a given amount of latency, right? If the load always takes one cycle. If the branch always takes one cycle. But in many cases, that information, there's some information the compiler doesn't know. And software scheduling, as a result, is very difficult. Now, we're not going to cover software-based scheduling in this course, but if you take the advanced architecture course, you will see it. Or if you take a compiler's course, you will see that. But it's good to know what information is not visible to the software. Can anybody guess? I've given you one example, right? The branch directions, for example. It's actually going to be one of those. What else? Yes? The value stored. That's right, the value stored. The value is not available to the compiler, and that value may affect the latency of an instruction, actually, depending on how you design the hardware. For example, I'll give you one example. If you know that the value of a register is 0, source register is 0 for a multiply instruction, you don't need to fire up your expensive multiplier. You just check for 0 and you say, oh, the result is 0, because I'm multiplying by 0. If you know that the value is 1, you just copy the source register to the output. The latency of that multiplier, that intelligent multiplier, is dependent on the value of the source registers. And that latency is determined at runtime. Unless the compiler can analyze the values and figure out all of the values or the necessary values, it doesn't have this information. Because this value is usually supplied at runtime, depending on, for example, the input to the program, or input or a file, or somebody typing something, right? Basically anything that's determined at runtime. And there's usually 3 pieces of information, which is variable length operation latency, which is dependent on value. This is one example. Another example is if you have a cache in your processor, which we will hopefully talk about later on in the course, but basically your memory access may not always be a single cycle, right? In fact, it's not common that you have a single cycle memory access, because you may have a cache miss. You may actually bring the data into the cache, and then you may not find it, the load may not actually find it over there. As a result, you need to go to the main memory, which takes hundreds of cycles. Now you have a variable latency operation, right? Sometimes the value is closer to the processor, sometimes the value is far away from the processor. Right? Again, the compiler doesn't know this, right? Memory address is also something that the compiler doesn't know because it's dependent on the values, right? And memory address could be useful in scheduling instructions. So, for example, if you want to order an instruction above another instruction, and if you have a load instruction and a store instruction, you need to figure out that basically the compiler needs to decide whether it can order the store instruction and have it execute first. For the compiler to be able to do this, it needs to know that the load instruction, wait a second, let's do the store and load. You have a store instruction and you have a load instruction. If you want to order this load instruction early, you need to know that this load instruction is independent of the store instruction. Right? It doesn't need the value. Now the problem is that memory address is calculated at runtime based on a register. And that register value is not available to the compiler. As a result, it's very difficult for the compiler to decide that it will guarantee correct operation if it does this ordering or reordering of operations. So because the late value or anything, or the thing that you're looking for is determined or dependent on a runtime characteristic. Now, if you take a compiler's course, you will see that modern compilers are extremely sophisticated. So they jump through a lot of hoops to actually guess whether or not that load can be ordered before the store. How do they guess? Well, they actually do analysis of dependencies, analysis of not the values necessarily, but whether or not the addresses will overlap, first of all. If they can guarantee that the store address will not overlap with the load address, they can order the load instruction and guarantee correctness. But of course, there are other things that they need to ensure, like the precise exception semantics that we will talk about in a little bit. Okay, so the software-based scheduling is actually very difficult, and there have been a lot of methods that are developed to overcome this somehow. So how can the compiler alleviate this? I'll give you another fundamental principle: estimate the unknown. So how does the compiler figure this out. For example, the branch direction is not known to the compiler, but the compiler wants to make a guess. There's something called profiling. It profiles the program. Profiling means somebody supplies the compiler with an input set, and the compiler runs the program. You could do it as a programmer also, actually. But the compiler runs the program and figures out, oh, this branch is always taken. I never see this branch not taken. Right. So I'm going to optimize the code as if this branch is always taken. And if I'm wrong, I'm going to insert a check into the program just to check if I'm wrong. And if I'm wrong, I'll jump out somewhere else. And there have been many optimizations that are proposed that way that are dependent on this profiling information. And the compiler reorders the code and also inserts hooks into the code saying, well, if this reordering is wrong, do the correct ordering this way. Now, if you optimize your code well, this actually buys you a lot of performance because you really optimize your common path, if you will. Okay. Again, I won't go into this in detail, but you should really know the terms. Profiling is basically the action that the compiler does to try to alleviate the information that it doesn't know at runtime, but try to discover what could happen at runtime. Does that make sense? At the high level, at least. You may not know exactly how that reordering is done, and that's not the subject of this course. But if you're excited about this, you should definitely take an advanced architecture or compilers course. Okay, so let's move to the second key issue in pipelining and precise exceptions. But maybe I don't want to move here. Okay, let me actually move until we hear the bell ring so that you can think about it during the break. Basically, there's one issue that we sidestep. Not all instructions take the same amount of time for execution. There may be some instructions that take 10 cycles, there may be some instructions that take 1 cycle. If you require the pipeline to take 10 cycles, that's a bad idea. Basically, the idea is to have multiple different functional units that have different number of cycles. So basically, your pipeline now starts looking like this. Your integer add takes 1 cycle, integer multiply, if you're lucky, takes 4 cycles. Floating point multiply takes much longer. Load store can take much longer, depending on where the data is. And the divide operation can take 50 cycles. Now it doesn't, so these units can be pipelined or not pipelined within themselves individually. So if you have a pipeline structure like this, you can let independent instructions start execution on a different functional unit before a previous long latency instruction finishes execution. So you may have a long latency floating point multiply that's going through your pipeline, and an independent integer multiply that started over here, and an independent add that started over here. Now you have concurrency in your pipeline, right? Now there's a problem with this. Basically, because of this, let me finish this and then we'll take a break. Because of this, your execution may look like this, right? If you don't change anything in your pipeline, and I have a question mark over here, that's a write state, you write back the result. Your execution may look like this. You have the floating point multiply and an independent add, and this is your time over here, and this is what you fetch. And then another floating point multiply and an independent add, and these are all adds that are independent. In a von Neumann architecture, I will assert that this is wrong. Why is this wrong? Yes?
Because the writes should be sequential.
Exactly. Basically, we've updated the architectural state in a non-sequential manner. In von Neumann architecture states that every instruction should finish sequentially. Right? Whereas here, the add instruction wrote the register file before the multiply, whereas the multiply came earlier in the program order. Basically, we did not preserve the sequential semantics of the ISA, and that's a problem. That's one example of a problem is what if this floating point multiply incurs an exception? If it generates an exception, I should have made the divide maybe. Divide by 0 gets an exception usually. Basically, if it has an exception, now you updated a lot of registers over here. And now if the programmer tries to figure out why does this exception happen, what's the state of the architecture at this point, they may go crazy, right? because you updated the architectural state, whereas the programmer is relying on the fact that you can only update the architectural state when an instruction finishes, and you do it sequentially for every instruction. So that's the reason why we have precise exceptions, and that's what we're going to cover in the remaining half. So we can come back in 15 minutes. Now it's 14.
Okay, let's have 10. This way we will start again earlier. Do you have any questions? Okay, let's continue in 10 minutes.
Okay, let's get started. So now we have a problem at hand, right? We have this multi-cycle execute machine, but it's finishing instructions before they are supposed to be finished. It's not supposed to finish, you're not supposed to update the register file, architectural state, before the previous instruction is complete. Right? So how do you solve this problem? Well, before we decide to solve the problem, first of all, let's discuss why this is important. To understand why this is important, we need to discuss the concept of exceptions and interrupts. Again, these are very fundamental concepts. Unfortunately, some people, including some important ISAs in the world, don't distinguish between these two things. I like distinguishing because I think it's a better principle to distinguish two different things and not name the same way. So some people call these interrupts, some people call these exceptions, whereas there are two different kinds of things, and I'll call them exceptions versus interrupts. And the differences between them are cause. So one of the most important differences is cause. Who's causing the event? So these are basically, I will say, exceptional events in general. The cause of an exception is internal to the running program. Basically, an exception happens because an instruction got a value that you cannot operate on. So for example, you cannot divide by 0. Dividing by 0 it's basically not defined, right? So that's an exceptional condition. And that's caused by the program itself. The instruction itself caused that problem, right? It's not coming from the outside, external world. An interrupt, on the other hand, its cause is external to the running thread. A program is running, externally some user decides to hit the keyboard, or, I don't know, move the mouse, but the processor is busy doing something else, right? So the processor needs to be interrupted. By the way, these are interrupts are a very von Neumann concept. Exceptions are not, if you think about them. An interrupt is an interrupt because von Neumann processor is a single processor, and it's doing something, and you need to interrupt it to do something else. Now let's stretch our minds a little bit. If you have a data flow computer, an interrupt is just another data input to a huge data flow graph, which is your execution environment in the processor. Right? Whereas exception, because it's internal to the running program, an instruction, for example, it exists in all paradigms of computing. You can always get a divide by 0 in a data flow computer or a von Neumann computer. Does that make sense? So the cause really determines whether something is an exception or interrupt. Now, cause also enables you the flexibility to when to handle these things, or inflexibility. If you get an exception, well, you'd better handle it when you detect it. If you're dividing something by 0, if you don't handle it at that moment, and you know that it's really a true divide by 0, it's not based on it's not done because you're in a speculative path, because you predicted a branch incorrectly, then you'd better handle it at that moment, because something else may depend on it later on. Whereas interrupts, most of the time you can handle it when it's convenient to do so. You don't have to interrupt the running program right at that moment to get a keyboard input, right? Or a network packet comes. You don't necessarily have to process it right away in the processor by kicking out some other program, right? You can handle it when it's convenient. Of course, when you handle it depends on the interrupt processing latency. For example, if you're doing packet processing on your CPU, your packet processing latency depends on when you decide to process that packet coming from the network, right? But there are some interrupts that are very high priority that you'd better handle very quickly. One example is power failure. That's an interrupt. If power fails, somewhere here, there's an interrupt that's generated to the processor saying power is failing. It's up to you to do something about it. And the processor may decide to write data into persistent state such that everything is consistent, right? But we're not going to deal with those system level issues now. Again, that's an advanced architecture course. Or machine check when there's an error. Usually if there's a bit flip in memory and it's not corrected, it cannot be corrected, there's a machine check interrupt. This is the name of the interrupt. It's called machine check. That gets generated, that signals the processor. Again, this is usually a high priority one because if there's an error in your memory, you might want to do something about it before you do something else, because you may end up reading that part, right? Okay, so there are other basically priority of exceptions and interrupts are different. Priority is the priority of the process for an exception because it's really internal to the process or the running thread. And for interrupt, it really depends, right? How important is this interrupt? Power failure is very important, but something else may not be as important, right? And handling context. You don't need to know these as much, but these are the really fundamental ones. Basic handling context means, because it's internal to the thread, it's really, how do you handle it depends on the context of the thread, architectural thread. Yes? So that's, we didn't cover exactly how it could do anything, but it could, for example, well, maybe not the process, because the process, remember, power failure is an interrupt. Maybe the process doesn't do anything, but you want to kick out the process. Basically, when to handle means when do you actually start doing something about it, right? When the power failure comes, you want to handle it instead of, not when convenient, but maybe immediately, right? Does that make sense? Yes. So the system needs to do something about it, perhaps. Okay. So let's get back to handling context. So the process handles the exception, whereas the system handles the interrupt. So you bring me to my point. That's good. The handling context is the system for the interrupt, whereas for the process, it's really the exception. Whereas for the exception, it's really the process. Okay, so in most cases, existing machines don't get interrupted if you get an external interrupt, they wait for a while. They at least wait until they finish whatever instructions are in the pipeline and drain the pipeline, and then they handle the interrupt. That makes sense because you've already done a lot of work to process some instructions. You'd better wait for a while and then handle the interrupt after you finish that work so that you don't waste power. But exceptions, you've got to handle them right away. Okay. So what's precise exceptions and interrupts? Basically, the architectural state should be consistent or precise, as I will define it in a little bit, when the exception or interrupt is ready to be handled. So what does this mean? In the von Neumann architecture, all previous instructions should be completely retired. Retired means finished and updated the architectural state. Architectural state is registers, architectural registers, and program counter. And no later instruction should be retired. Basically, you have a clean slate between two instructions. Anything before this instruction is done completely and update the architectural state, and anything after this instruction has not started yet, done nothing to the architectural state. So retire is also used as commit. You'll see this terminology. It means finishing execution and updating the architectural state. Some people also call it graduate. I guess it's similar to graduating from college or somewhere, but I don't like that term as much. And it's not as commonly used also. So let's see what happens. First of all, before we go into this how do you support it? Let's see what happens when you actually decide to handle an exception, let's say. Basically, we're going to look at exception right now because interrupts, as I said, it could be handled when convenient. So when the oldest instruction in the pipeline that's ready to be retired is detected to have caused an exception, the control logic needs to do multiple things. First, it needs to first ensure that the architectural state is precise, as we've discussed in the previous thing. This means register file, PC, and memory are not updated by any later instructions. They are completely updated by all previous instructions. It flushes all younger instructions in the pipeline, such that the pipeline is cleared for processing the exception handler, which is the exceptional thing that you need to do to handle the exception. It saves the program counter and the registers as specified by the ISA. Most ISAs, all ISAs actually define how to handle exceptions and interrupts. Basically, they say you need to save the program counter to the stack, you need to save the registers to the stack, and such that you can go back to it when you resume the process. And it redirects the fetch engine to the appropriate exception handling routine. Basically, depending on the type of the exception, it finds a program counter and it loads that program counter and the architectural registers as needed to execute some exception handling code. This could be system level code, basically. For example, when you get a divide by zero, you could have an exception handler that's a specialized one that tries to check why you got the divide by zero. And then it can, at the end, maybe it fixes that divide by zero somehow. Don't ask me how. Maybe there's some program logic. Programmer can write some of these exception handlers also. But at the end, you can, it finishes and it either aborts the process that's executing, or it goes back to the process after handling the exception. Later, we will see virtual memory, which enables the programmer to see large amounts of memory, and you get exceptions in the virtual memory. Access protection exception is another one. You have a load instruction that's trying to access something that the process does not have privilege for. It needs to be handled somehow, right? Again, that handling is very specific to the system that you're designing. It's also very specific to the program, if the program can do something about it. Okay, so these are the things that need to be done when you get an exception. So at the end of the exception or interrupt, the operating system can decide to reschedule this thread that was running, and basically what it does is it basically reloads the PC, program counter, and the registers, and the process resumes from where it left off, basically. It's as if nothing had happened. Although something has happened, somebody handled the exception, somebody handled the interrupt, and the process now can come back and resume. It can resume only because we have this precise exceptions, right? Make sense? Because we were at that boundary of that program counter, and the registers were updated with everything before that program counter in the sequential execution stream, and they were not updated with anything after that program counter, any instruction. Okay, so why do we want precise exceptions? So this is sometimes a debate, but first of all, because the semantics of the ISA require it. If you have this contract, you'd better obey the contract, because people may write software that assumes the contract, and if you disobey the contract, they will come at you. And for good reason, because you made them crazy, perhaps, right? So basically, there is a contract. This is basically the very legalistic, if you will, approach. This contract needs to be obeyed. But why is there a contract? Why is this in the ISA, in the ISAs that obey the von Neumann model? It's not in the contract in the data flow. There's no precise exception in the data flow. And that's exactly why data flow machines are very hard to debug. So first reason of having precise exceptions is aids software debugging, basically. As I told you earlier in this example, let's go back to it very quickly. If you have imprecise exceptions, if for some reason you get a fault over here, an exception over here, now you need to debug the program. Where do you even start? Because these instructions may have updated the architectural state, so you don't know which instructions have updated and which instructions have not updated. And this may change. Even if you know the pipeline structure, this may change because you may have dynamic latencies, as we discussed, right? The latency of an instruction may change depending on the values, depending on the events, depending on whether or not your memory access takes 1 cycle or 5 cycles or 10 cycles, based on your cache hierarchy, based on your memory. So it becomes really, really hard to debug. You really want a clean slate to be able to debug. Make sense? And this is really perhaps the most important part of it. Now, there have been machines that were designed. This is not really absolutely necessary, really. You could actually take the state of all of the pipeline registers and expose them to the programmer. And there have been machines that were proposed and designed that do that. They don't have precise exceptions, but they say, okay, I don't have precise exceptions. I'm not going to be bound by, and there are reasons why not precise exceptions also. Performance could be an issue, right? As we will see in a little bit. The machine says, programmer, here's my microarchitectural state. Here are all the pipeline registers. Good luck. Figure out what happened on your own. Debug your program. Sounds bad, right? You don't want, it's already hard to write programs to begin with, write correct programs. If the debugging is even harder than that, then you have a problem. Right? That's usually a bad design choice. In fact, IBM 36091, which was a brilliant machine that was designed in 1965, that's the first machine, that's the second machine in the world that had out-of-order execution, second known machine that had out-of-order execution in the world. Tomasulo's algorithm, Robert Tomasulo invented the algorithm. It did execute instructions out of order, but it didn't have precise exceptions. As a result, it really didn't take off. Basically, programmers went crazy and they couldn't program it. Even though it was very high performance, nobody really used it except for some really smart programmers who figured it out somehow. The reason out-of-order execution became very prevalent in all computer architectures was because somebody later in the late 1980s, mid-1980s, said, okay, we want to have out-of-order execution, but we want to support precise exceptions. We want to execute out of order to get high performance, but we want to report the results in a precise manner to the architectural state, to the software. And once you combine out-of-order execution with precise exceptions, all machines became that way, and everybody now can program them. Even though the concept of out-of-order execution itself was developed in 1960s. So that's critical, because if you think about the hardware design world, there are very few hardware designers in the world. It's a lot, but it's still very few compared to the software designers in the world, right? There are many, many software designers, and most of them you may not know what they're doing. They may not even know how to debug their programs, even if they have precise exceptions, right? But if you have precise exceptions, you make it easier to debug, then you make life easier, so you enable your systems to take, to be used by others. So this is a critical one. There are other benefits. It enables easy recovery from exceptions. If you have an exceptional condition, having precise exceptions helps because it's easy recovery. You just need to guarantee this invariant that we've just discussed, right? It enables easily restartable processes. Basically, you can restart the process easily. You just basically load the program counter and the registers. That's it. Again, this is not necessary. You can, again, dump the microarchitectural state and reload the microarchitectural state entirely, right? And there have been machines that have done that also, but that's usually a bad idea. It's not a very good design. And finally, it enables things like traps into the software, which we're not going to get into. Basically, if you have, for example, if you have an instruction that's not implemented in your hardware for some reason, but it's in your ISA. And there are cases that may happen because you say, oh, I'm not going to support this in hardware anymore because no one is using it. So I'm going to implement it in software. So the way you implement is it's basically a trap into the software. Whenever you see an instruction, it becomes a trap and it gets emulated in software. A lot of virtual machines work this way, actually. So if you want something like that, you're really switching to some other place in the code. You really want precision. You don't want some other instructions that are coming later to have updated the architectural state that you're going to mess with in that instruction in software. So you can do really interesting things if you have this precise exceptions, because you start with a very clean state. Okay, so how do you ensure precise exceptions? Hopefully you're convinced that you want this. One option is to make each operation take the same amount of time. Even though an integer add requires only 1 cycle, you make it take 8 cycles. Not 8 cycles. You make it take the worst case instruction latency. If a load takes 500 cycles in the worst case, everybody takes 500 cycles and goes through this pipeline. Sounds bad, right? Well, clearly that's bad. Memory operations take a long time. Each functional unit takes worst case number of cycles. That's a bad idea, and that's why no one does it. So people have proposed solutions to this. Actually, the paper you're reading, not this one, this is the original paper that proposed 3 of these things over here. The paper you're reading talks about some of these, so I would definitely recommend you to read it. We're not going to cover these 2, and these 3, you're not going to be responsible for this. But I'm going to cover the first one, which is employed. Modern microprocessors actually employ all of them in a complicated manner. If you want to know exactly how they employ them, you've got to take my later architecture course. But we're going to cover one of them, but even that one will be interesting, hopefully. Yeah, it's amazing what goes into a modern out-of-order processor. You really need to do all of these to get high performance, basically. Okay, so we will not cover these, but we'll cover this first one. Basically, the solution idea is very simple. It's you finish instructions in the order they finish. An add takes 1 cycle, that's good. It produces result after 1 cycle. And you store the result somewhere, but not in the register. The idea is complete the instructions in out of order, but reorder them before making the results visible to the architectural state. Hopefully this makes sense. Yeah, let me do this so that I can see better. So we add another instruction into the pipeline. After an instruction completes, it writes its result into this reordering buffer, as opposed to directly writing to the register file, because the register file is visible to the programmer. You write it over here, and when the instruction becomes the oldest one, you take the value and write it into the register file at that point in time. So it's simple. This way, instructions can complete in any order over here, but then you reorder them before making them visible to the architectural state. That's true for the memory also. I just don't show it memory. So whenever a memory operation, let's say a store, finishes, it writes its result into the reorder buffer, and then updates memory when it's really the oldest instruction in the machine, and it doesn't have an exception. Okay, so how do you make it work? So you have the structure, it's a linear array that basically contains status of each instruction. It's like memory, but it basically stores a status. When an instruction is decoded, it reserves the next sequential entry in this linear array, in the reorder buffer I'll call drop. When the instruction completes, over here, it writes its result into the reorder buffer entry. And when the instruction becomes the oldest in the reorder buffer, and it has completed without exception, so there has to be a finite state machine that checks this every cycle. Is this oldest instruction done? Has it written its result? And does it have an exception? If it has its result written in the reorder buffer and doesn't have an exception, then basically that finite state machine takes the result and moves it to the destination register of the instruction. That's the idea. It's very simple. Or memory. Memory is just a bigger version of the register file from this perspective. Okay, so basically, this reorder buffer structure buffers information about all instructions that are decoded, but not yet retired or committed or finished. Finished in the sense that they're out of the machine. So it needs to be big, as many instructions as you can support over here. Right. Every instruction that's decoded goes into the reorder buffer, and you take out the instruction when it actually is the oldest instruction. So just to give you an example, today's processors have reorder buffers of size about 250 or so. And it's increasing sometimes. Sometimes it's reducing also. Okay, so what's in a reorder buffer entry? Very quickly, basically you need all the information that's about an instruction so that you can keep track of the instruction status and write to the destination. So of course the reorder buffer entry can be valid. If you're writing to a destination register, you need to store the destination register ID. You need to store the destination register value when it becomes available. If you're storing to memory, you need to have the address. You need to have the data when it becomes available. You need to have the program counter of the instruction so that if there's an exception, you use that to report to the user. And there's also some other valid bits for these things and control bits. And of course, an entry that says whether the instruction has caused an exception. Yes? So it's not that it's faster. It needs to be there so that you update the register file in sequential order. Okay? There's no real speed. Actually, we'll talk about the speed later on. It's actually slower if you want to get the registers out of there. Okay? Okay, yes?
Let's say the first instruction is a load and the second one is an addition. Wouldn't the addition still need to wait until the oldest one is finished? So wouldn't the addition still need to wait for 600 cycles?
That's right, yeah. So if there's a dependent instruction, the pipeline stalls anyway. You don't get into the situation if there's a dependent instruction. You get into the situation if the instructions are independent, but they take different amounts of time, right? Because remember, we're still in an in-order pipeline. If you're decoding an instruction and if the destination register value is not available yet, you stall the pipeline. Make sense? We're going to fix that problem later on in this lecture when we talk about out-of-order execution. Okay, so basically the reorder buffer needs to store everything that's required to correctly reorder instructions back into the program order. And we have a clear program order, as you know. Everything that's required to update the architectural state with the instruction's results, if the instruction can retire without any exceptions or any issues. And also it needs to have information to handle an exception interrupt precisely if an exception or interrupt needs to be handled before retiring the instruction. So the color coding is because of that a little bit. So you need all of this to update the architectural state. You need the program counter so that whenever there's an exception, you need to report that to the user. This program counter had an exception. And of course, the bit, you need to also have that. And then also you need to have these control bits to orchestrate everything. Okay. So you of course need to have valid bits to keep track of the readiness of the results. For example, if this reorder buffer entry is for an add instruction that has a destination register, whenever you decode the add instruction, you set the valid bit of the reorder buffer entry, you set the destination register ID, but you don't have the value yet. The value gets produced later when the add gets executed in the pipeline. At that point in time, you set the valid bit associated with this destination register value, which is stored somewhere over here. And for an add, the finite state machine at the end checks if the add is valid, and if the destination register value is valid, then the add is done. And if there is no exception, that's good. And if it's also the oldest instruction, then you can write the destination register value to the destination register ID in the register file. Okay, so conceptually it's very simple, but you need hardware to implement it, of course. So what does this enable? Basically, it enables this picture. Assume these instructions are independent again. If you have a dependent instruction, so if the second instruction is dependent on the first instruction, you don't have this picture. Because this instruction, remember, we're using scoreboarding or some other kind of dependency checking. If this instruction requires a value that's written by this instruction, this needs to wait at this point, and it cannot proceed to execute. So you need to keep this instruction in decode stage until this finishes execution. That picture is different. This picture is for instructions that are all independent of each other, and there are cases where instructions are independent of each other. Okay, so what happens here is, now this instruction takes 8 cycles. It writes its result into the reorder buffer after that, and then after that it writes the result into the register file. So this is the reorder buffer write, and this is the register file write. Now this instruction, independent, it can execute, it's an add. When it's done, it writes its result into the reorder buffer, and it basically waits over there. And when this instruction is done, this becomes the oldest and can update the register file, right? This way you don't need to lengthen the execution of this instruction. You basically write the result into the reorder buffer. As you can see, these are all adds, and this multiply takes 8 cycles. So the key thing over here is the writes are moved over here. The register file updates are moved over here so that they're in sequential order. So now the programmer doesn't go crazy. Okay. So there's a key question over here. What if a later instruction needs a value in the reorder buffer? If there's a dependence. This is not the case over here, but assume that there's some other instruction over here that you're fetching. It needs the value that was written by this instruction, let's assume. The value is there in the reorder buffer. But what do you do with that instruction now? It's actually produced, right? You know that, let's assume that this is writing to R2. The second instruction is writing to R2. It's written the version of R2 over here into the reorder buffer. Let's assume that we fetched an instruction that needs R2 over here. Do you stall that instruction? Or do you somehow grab the value from the reorder buffer? If so, how do you grab the value from the reorder buffer? Well, one option is stall the operation. It stalls the pipeline. So basically, at that point in time, whenever you have a dependent instruction, you just stall. After that, you need to wait until the value is written into the register file so that this imaginary instruction that I added can proceed. Not good for performance, right? So another option is to actually, you know that the value exists somewhere in the reorder buffer, so why don't you read the value from the reorder buffer? It turns out it's not very easy, so we're going to develop methods to actually read the value, and all existing processors do this. Those methods exist, but it's going to complicate our machine even more. So why do you want to do this? Because there's no reason to stall this instruction. The value has already been produced, right? You're just waiting for that value to update the register file, but if you actually read the reorder buffer, you get that value, and you can continue execution. You can keep filling the pipeline. So how do we read the value from the reorder buffer? Basically now, there are multiple places where a result exists in the pipeline. Recall in the past, a result could exist in the register file, when it's written to the register file. A result could exist somewhere in the pipeline, and it could be bypassed. Remember forwarding of data, bypassing of data last week? It could be bypassed. Now, a result can exist in the reorder buffer and nowhere else, right? If an add has finished execution, it's written its value over here. The value is over here. It's not here because the add is done. It's not here because the add doesn't update the register file yet. So the value is over there. So a value of a register can exist in different places. And we need to be able to, if you want high performance, you need to be able to get it from different places. Remember, we introduced a bypass path so that you can get the value right after it's produced, so that the instruction doesn't need to wait until the value is written into the register file. If the value is produced over here in the function unit, just bypass it so that this instruction can continue executing quickly. I don't know what happened here. Okay. So now some value can be here. Okay, so the question is, how do we actually read the value in the reorder buffer? Basically, now we have, I've shown you an example over here. When an instruction is being decoded, you can have these two paths. You access the register file, and you also access the reorder buffer at the same time. Now, this access is actually easy. You have a source register, R3, let's say. This is, we'll see the memories later on, but this is called a random access memory, meaning we've seen this type of memory before. If you have a source register, R3, you used R3 as the address, index the register file, and register file gives you the data, right, for R3. That's easy. And you have a linear array. But in reorder buffer, you cannot do that. The ordering of registers is not in any order over here, because what this is really an ordering of the instructions. An instruction may be writing to registers 10, the next instruction may be writing to register 5, the next instruction may be writing to register 50, if you have 50 registers. So basically, the value, the address you're looking for is really inside the content of each entry. You cannot just simply index this. You need to search in this hardware structure. So this is actually content addressable memory. So you need to search this memory with the register ID, which is part of the content of an entry. Let me give you an example quickly of this, because it's easier to look at an example over here, I think. If I can switch to the DocuCam. If the DocuCam is good for... Okay, let's see. So basically, this is the... Let's start with the register file. Okay, that's good. This is the register file, right? You get register source 1, and let's assume that it's R3. This is all in order. Register 0 is here, you get 32 bits, let's say. Register 1 is here, register 2 is here, ... assuming you have 32 registers. What do you do to get register 3? Remember, you have an address decoder, you index using this address, and the address decoder activates this word line, and you get those 32 bits. Nice, it's simple. Now, the memory we have in the reorder buffer is completely different. Reorder buffer. Remember, each entry had a valid bit. This entry 0, entry 1, entry 2, ... This is not the register ID. This is the ordering of the instructions. And remember, we have the destination register ID, assuming an instruction is writing to the register. It's stored in all of these locations for each instruction. So what you need to do if you want to ask for register 3 over here is to, let me do it in a nice way. What do you need to do? You can oh, okay. Can you see? Okay, let me actually shift to another one over here. If you want to do this, you need to compare, right? You have a value over here, which is the destination register ID of different instructions. You need to take this, ask if it's equal. That's not enough. You need to do it for every single entry. Ask if it's equal. Ask if it's equal. Ask if it's equal. And if you have 126 entries, like in Pentium 4, you need to do it for 126 entries over here. Doesn't sound like fun, right? I don't know how to do this. Okay. So basically, this is the difference between, so you need to do it basically for every single entry. And if one of them matches, then you have register 3, and you've gotten register 3, destination register ID, and also you have the destination register value. And if there's a match, you take the destination register value. Clearly, now this becomes not so easy to implement, right? Think about how to implement this in logic. You have these matching lines, and essentially you can have a huge mux, right? Where every single destination register value is connected to that mux. That's a lot, maybe 126 of them if you have 126 of these. And then the matching one selects the one that you really need. So basically we're searching for R3, register 3. Make sense? Yes?
If there are multiple R3
There are multiple R3 entries, you take the youngest one. Right, exactly. So now you're thinking ahead, that's good. This structure allows you to have multiple R3 entries, right? So whenever you have an instruction writing to R3 and another instruction writing to R3, they can have multiple R3 entries because they're in different locations. So remember, what is that? That's a write after write dependency. That's not a real dependency. So you can actually have different R3s over here. Okay? Okay, so you need to take the latest one. So it's actually more complicated than just a search. It's a search for R3. It's an ordered search. You need to search for the latest one. Okay? Yes? Oh, okay. Now you're thinking even more deeply. How do you remember which one is the oldest? Well, hopefully there's an ordering of this, right? So what you need to do is really a queue over here. There's a head pointer and there's a tail pointer. And tail pointer is the oldest one. And the head pointer, tail pointer is the youngest one, and head pointer is the oldest one. Okay, and then you need to, it's really a circular queue that you're implementing in hardware in the end. Because you cannot do it with a fixed structure that is not circular. Okay, so hopefully this gives you, so this is basically the key difference between, this is, maybe I need a different kind of pen. Let's see, I have green here, I don't know if it works. So this is really random access memory, RAN, and this is, reorder buffer is really content addressable memory, CAM. Why? Because in random access memory, the address is the address of the entry, the address you're looking for. It's easy to access. Here you're looking for something that's inside the content. That has nothing to do with the address. The address is all these 0, 1, 2, 3, up to 125. But the content you're looking for is R3, which is really stored inside the content data. So you need to build this sort of structure to get the content, to match the content. Okay. Okay, so that's a reorder buffer access for you. Let me go back to wherever I need to go back to. And now, when an instruction is decoded, it needs to access the register file and the reorder buffer. And if R3, let's assume that you're looking for R3, is here, you get the value from the reorder buffer. If R3 is not here, because this is the youngest definition of R3, right? But you need to have an ordering over here also, because the value may actually come from the bypass path. The R3 may be here, but it may not be produced yet. It may not be valid yet. There might be another instruction that hasn't written to it. So then you actually get it from the bypass path. And if there is no instruction that's writing to R3 inside the reorder buffer, and if there is no instruction that's executing over here that's writing to R3, then you get the value from the register file. So a value can be present in different places, as you can see. Okay, any questions? This is really important. This is going to be important for us in out-of-order execution also. Okay, so this doesn't sound very good, because now my critical path may increase, right? If you look at the reorder buffer, I'm searching for R3 here. Actually, I'm not just searching for R3. I have two sources if I have a binary operation, right? I need to search for the source register 1 and source register 2. So this picture that I showed you over here becomes even more complicated. You don't need just one comparator for each destination register ID. You need two comparators for two sources. So it becomes even more expensive now. And also, this latency of the reorder buffer, search latency is much slower, because you need to go through, if you remember, all of these comparators and this huge mux multiplexer at the end. So the latency of the reorder buffer access is much longer. So what people do is trade off to reduce the critical path of this access is to use indirection. Yes?
So the reorder buffer holds the youngest values of this register. But
yeah.
if you search for a certain register, you take the oldest.
No, you need to take the youngest one. You're just fetching this instruction. You need to take the value that's produced by the latest instruction in the program, right? So, okay, let me actually show you a picture over here very quickly. DocuCam. So, let's assume that you have a bunch of instructions that is writing to R3. Multiply R3. I don't know, divide, and the destination is R3 always. Now you're fetching an instruction add. This is the one that you're fetching and decoding. It needs R3. You need to get the youngest one, right? Because that's the program order. The oldest one you don't care about, actually. This also shows that this R3 has nothing to do with this R3, probably, right? Unless there's a dependence. Okay, we'll get back to this. But you need to get the youngest value. Okay, so how do we actually get rid of this reorder buffer search from being on the critical path? You use indirection. So basically, you augment the register file to be a little bit more intelligent. You access the register file first, and check if the register is valid. Remember the valid bits in the register file that we introduced for scoreboarding? We still have those valid bits. The register being invalid means that the register is being written by someone. And if the register is invalid, that means that it's somewhere in the reorder buffer, and the instruction is either executing or it's finished. So you access the reorder buffer after that. Now the reorder buffer doesn't need to be content addressable anymore. So you can actually have an indirection that tells you which location in the reorder buffer is going to produce this R3. So how do you do that? If the register is not valid, it must be coming from an instruction that's somewhere in the reorder buffer. The register file then stores the ID of the reorder buffer entry that contains or that will contain the value of the register. Right. So basically now we've mapped a register to a reorder buffer entry. Register file maps the register to a reorder buffer entry if there is an in-flight instruction writing to that register. So let me actually do this since we built, not that one, DocuCam. Okay, DocuCam doesn't want to come. I don't know how to zoom out more. That's it. That's the best we can get, apparently. So basically, this is content addressable. We need this so that we can access reorder buffer entry and register file in parallel. But if your register file is slightly different and you use indirection, this is what we can do. So this is our register file. This is our reorder buffer. 0 through 31 again. And now register file has val bits. And if the val bit is 1, you trust the value because someone has written it. If the val bit is not 1, let's assume this is register 3 that we've been using. This is not 1. That means someone is going to write to this register. Who's that someone? That someone is the instruction that's allocated into reorder buffer entry, essentially of the writer instruction. So for example, if you're decoding add, that writes into R3, R4, I5. We'll ignore this for now. What you do is you need to allocate a reorder buffer entry for that add. You have a head pointer over here, which we introduced, and then a tail pointer. You allocate this add instruction, allocate a reorder buffer entry in the youngest location, and then increment the tail pointer. And then basically say this is valid, it's writing to R3, R3 is not available yet, ... And also say R3 is not in the register file anymore. Even if this was 0, it's still 0. If this was 1, you turned into 0. R3 is not in the register file anymore. Don't trust the value that's here. It's garbage, because somebody is going to write to that R3. For every later instruction, R3 is going to come from this instruction that's going to be in that location, the reorder buffer. And what is that location? I don't know, 255, let's say. Wherever that location is, basically, the tail pointer. I'll just make it a 131. You basically put 131 over here. This means that register 3 is not in the register file. It's going to be produced by this instruction that's in reorder buffer entry 131. Make sense? Now, the designer of this is happy, and the designer of this is happy, because you don't need to search for R3 in a content addressable way over here, right? You just turned the content addressability into a random access with an address because you added a level of indirection. That's the beauty of design. So you added a level of indirection so that you get rid of the content addressability. Make sense? Yes?
How does the reorder buffer behave in regard to flushing?
Flushing is easy. Basically, if an instruction has an exception, let's do that over here. Why is this so? Okay. So for some reason, let's say this instruction over here had an exception. You just get rid of all of the instruction in the end. You need to fix up the register file, which we're not going to talk about. Exactly. So that's a good question. You need to fix up the register file, but that's beyond the scope of what we're going to talk about. Existing machines fix up the register file. Yes?
So do you have to add more hardware to the register file? Like does each register have to be bigger now?
No, well, yes, certainly. The location is now bigger, right? It's not just 32-bit value, it's also the tag over here. I'll call this tag. It's a reorder buffer entry. But the register data value doesn't need to be bigger. Okay? Okay. So now you know how the reorder buffer behaves. And you know that it doesn't need to be content addressable. We've eliminated this. So this is a real example of a reorder buffer like what we've talked about. This is out of order. It's not in order, but you will see that. Remember the structure that we drew over here? That's going to be very useful in out of order execution soon. This is a real machine, Pentium 4, and Intel wrote this beautiful paper that talks about Pentium 4. Basically, this is the register file I kind of drew, except they put physically these are the values in the register file. They call it the register alias table, which we're going to also call it soon. These are the 8 registers in the old x86 architecture, not in x86-64. And basically, the values of the register can be in the architectural register file, a retirement register file, which is essentially this over here. Or they could be inside the reorder buffer, waiting to be written or already written by an instruction that's in the pipeline. Okay? So this is the indirection that you have. This alias table basically gives you an indirection as to where you can find the value. Okay, so this is important. Again, I think a lot of these things are important. Basically, what we've done is actually something really important in the sense that we've renamed this register. This register R3, it's just a name. We're referring to a value now. The R3 may come from this real place in the register file, or it could come from anywhere. As long as you get the right value, it's just a name, right? So basically, what we've done is we really eliminated the output and anti-dependencies. We'll talk about this. So these are not true dependencies. The same register refers to values that have nothing to do with each other. Remember, I showed you writing multiple instructions writing to R3. Right? These instructions are write to R3, but you really need the latest definition of R3 in the end. And they exist because they lack, you don't have enough register IDs in the instruction set architecture, because the instruction encoding is small, right? There's no reason to write to R3 all the time, right? Because this if you have infinite number of names, locations, you would always write somewhere else. That's why these are not true dependencies in the output. Okay, let me actually go to here first. So if you look over here, this is a true dependence. This instruction is producing R3, this instruction is consuming R3. There's a real data value need. This value definitely needs to be communicated over here. That's why this is called a true dependence or a flow dependence. You cannot eliminate these dependencies unless you change your algorithm somehow. Anti-dependence, this instruction is reading from R1, this instruction is writing to R1. There's no logical connection, right, in these data values. It's just a name. This instruction happened to read from R1, and somehow you write into R1 because you don't need the value that's inside that location, inside that name anymore. That's how you do it. You could have changed this to R1,000,000, and nothing semantically would have changed over here, right? Similarly, this output dependence, if you look over here, this instruction is writing to R3, this instruction is also writing to R3. These have nothing to do with each other semantically. This R3 is produced by this instruction, this instruction can produce a completely different R3, and they're not communicating with each other. That's why these dependencies are not true dependencies, they're called anti and output, and we've essentially eliminated them. How have we done it? Basically, the register ID is renamed to the reorder buffer entry that will hold the register's value. So we're mapping the register's ID to the reorder buffer entry ID. This is also called architectural register ID. Essentially, we're mapping it to a physical register ID. And after renaming, the reorder buffer entry ID is used to refer to the register. And this is going to be a key component to ensure that we actually get correct results when we execute out of order. So now we've eliminated this anti and output dependencies with this sort of renaming structure. This gives us the illusion that there are a large number of registers. So let me finish this, and then we're going to start with out-of-order execution. So basically, this is the pipeline we built. This is our in-order pipeline with a reorder buffer. You get in-order dispatch. So whenever you're decoding, you decode in order. If there is a true dependence, you stall the entire pipeline. But if there is a not true dependence, anti and output dependence, this pipeline still flows. Only in true dependences you stall. Instructions can complete out of order because of multiple cycle execution, and then you reorder them, and then you write to the register file when the instruction becomes the oldest. So in the decode stage, you access the register file and the reorder buffer, you allocate an entry in the reorder buffer in order, check if the instruction can execute, it doesn't have a true dependency. If it doesn't have a true dependency to any of the values over here that are inside, you can dispatch the instruction. And you know how to do that with scoreboarding, for example. In execute stage, instructions can complete out of order because of multiple cycle execution and different functional units. And when an instruction completes, it writes its result into the reorder buffer. And there's a state machine at the end that checks for the oldest instruction in the reorder buffer. If the oldest instruction is ready, and if it doesn't have any exceptions, its result is written in the architectural register file or memory. Otherwise, if there's an exception, when the oldest instruction is ready, you flush the pipeline and start from the exception handler. And this works beautifully. So let me finish with the advantage and disadvantage. So reorder buffer is actually really important because you need to reorder the instructions for the von Neumann model. It's conceptually very simple for supporting precise exceptions, but we've added significant complexity into the pipeline for reordering. So this is kind of like the von Neumann tax that we're paying for sequential instruction processing. We want high performance, but we need to pay this tax, hardware overhead, power overhead. All of these structures that we added are actually adding power overhead. But we're gaining something also. We can eliminate false dependencies now, anti and output dependencies. But of course, there are disadvantages, because if we want to get high performance, we need to access the reorder buffer to get the results that are yet to be written to the register file, that are produced but not updated to the architectural state. So you need to use either content addressable memory or indirection. Either way, content addressable memory increases complexity clearly, but it also increases latency because the timing is very long. Indirection also increases your latency, right? You access the register file first to get the reorder buffer ID, and then you need to access the reorder buffer. So there's an indirection, there's additional latency, except that latency can be broken into multiple cycles. That's good. So other solutions that we have not covered, and we're not going to cover, actually eliminate the disadvantages. So existing processors actually employ multiple of these. Definitely future file, checkpointing, plus reorder buffer. They combine all of these to get a better solution than just a reorder buffer. Like one of your colleagues asked the question, how do you construct the register file when you flush the pipeline? It's actually not that easy. And that's the idea of the future file, is actually to help that. But we're not going to cover. If you're interested, you can read the paper that I referenced earlier. So I think that's a good time to take a break.